Hello, everyone. I'm Boon Kiat, BK in short, and I'm a postdoc at the University of Connecticut. I'm going to talk about the entropic reasoning for the cosmological constant. It is work that I've done with my collaborators from the University of Edinburgh, which includes John Peacock, Sade Koshwa, and Britton Smith. So thank you for the opportunity for presenting my work in the Multiverse from Home conference. Here's the outline of my talk. So I'm going to first introduce the cosmological constant and how it has been problematic in terms of its reasoning and how it was actually accepted into the cosmological model of our universe. Then I'm going to argue the using cosmic star formation as weights to weigh universes of different cosmological constant. And in order to achieve that, we need simulations beyond redshift 0. And then after going beyond redshift 0, we need to extend it to counterfactual universes. And then I'll end off the presentation with some conclusions. Right, so let me start off with the cosmological constant. So we are familiar with the cosmological constant because it is the component that's responsible for the expansion of our universe. And it is the dominant component of the universe, making up 70% of the energy density. And it was first introduced by Einstein in his 1917 model of the universe. But in that model of his universe, he's considered the universe to be static, which is not true, as Hubble observed the expansion of the universe in 1929, as you see from the figure on the bottom, which is the distance, the velocity against the distance plot presented by Hubble in his paper in 1929. And from that point on, there were various models that's being proposed to describe our universe, ranging from Einstein, de Sitter. There's other models as well, varying the different amount of matter and cosmological constant or dark energy. So on the right, you see a observation proof of or a observational verification of what the cosmological parameters should be in our universe. So in using the supernova, that's done by the authors, they looked at how it will fit on this diagram using different cosmological parameters, which is denoted by the different line styles. And they find that it's more suited for a flat universe, which has 0.3 in omega matter and 0.7 in omega lambda. So from that point on, there were more and more refinement to the observations, which further proves or which further verify these cosmological parameters. But there's a problem with lambda. So if you approach lambda from the theory point of view, using the 0-point energy of the vacuum, we sum all of them up to Planck scale. We actually find that the density of the vacuum is 10 to the 92 kilograms per meter cube. But if we go through observations, specifically using the W map, for instance, we find that the rho vacuum is actually 10 to the minus 27 kilograms per meter cube. So what this means is there's 120 orders of magnitude difference between theory and observation. So how can we bridge this? How can we explain the value of the rho vacuum? So in order to do that, let me start off with something simpler, which is using Johannes Kepler's example. So he's done extraordinary work in determining the orbits of planets. And the one question that he's always obsessed with is, why is the Earth's orbit 149 million kilometers away from the sun? Why is it this specific value? And he tries to derive this based on the laws of physics. But instead of asking that question, which might be the wrong question, the right question to ask is, why do we humans find ourselves on a planet at this particular distance? So rather than trying to determine one number from the laws of physics, we know now that based on our observation of exoplanets, planets can be at a wide range of distances away from the host star. And So the right question to ask is why at this particular distance? So we know that if we are too close to the sun, we will not exist because of the heat. We'll be too hot, and then too far, the planet will be too cold, and we will not exist either. So there's a wide range of distances, but only at this distance it can support life. So this is the anthropic reasoning, and we can further extend this to universes. So instead of asking how we can derive a single number from the laws of physics, we can say, right, in fact, there's a range of numbers, but there's only a narrow range, a specific number that can support life. So this is known as the anthropic principle, and it's giving preferential existence of the observers. So it depends on what are the conditions suitable for life. So the existence of observers can make prediction about this lambda. And similar to what we can argue for the distances of planets, we can also argue this for the values of the cosmological constant. For example, using Weinberg's argument in 1987, the lambda cannot be too positive, extremely positive, nor negative, because on both ends, it's going to affect structure formation. If lambda is too positive, then the expansion of the universe is too rapid. And if it is too rapid, it's not able to form galaxies, and eventually planets, and that's why it's not going to support life. And if it is extremely negative, then it's going to recollapse upon itself before there's even time for meaningful structure formation to happen, and therefore it cannot give rise to life of our own. So we need the existence of observers to make predictions about lambda. That's basically what the anthropic principle is about. So in our case, we want to do that using the cosmic star formation. So why is the cosmic star formation important? So as I mentioned earlier, we assume that we need stars to form first, and then the planets to form after that. And based on the arguments that I presented earlier, there can be a wide range of distances, but they have to be in the right distance away from away from the star to support life. So this is we are assuming basically that observers are proportional to the amount of stars that we see in our universe, and this is tied to the cosmic star formation. So on the plot you see here presented by Maddow and Dickinson in 2014, we see a trend on the cosmic star formation where it peaks at redshift 2 and it declines down to redshift 0. And there's this functional form that you see that can describe this evolution of the cosmic star formation rate density. What is important about this is if it continues to go down towards 0, so if you go into the far future and the star formation rate density eventually goes down to 0, it means there's a finite area below the graph, which means that there's a finite stellar mass that's able to form in our particular universe. So using this, we can weigh different universes, and from there, but again, by assuming that the observers are proportional to the amount of stars that's formed, we can give anthropic weights to different universes. So that's why it's important for us to look at this cosmic star formation. And because our current simulations, which is the approach that we are using, is only interested in evolution up to redshift 0, we need to be able to push simulation code to go beyond our present time, which can be a technological challenge because they were not catered to resolve or to model galaxy formation beyond our present time. So there's a group that has done this using the Eagle simulation, and this is what they found in Salcido et al. In 2018. So on the y-axis is the cosmic star formation rate density, and on the x-axis is the age of the universe. So you can see for lambda CDM, which is the blue line, without AGN, the lambda CDM with the AGN, which is the solid blue line, it peaks at redshift 2, as we described earlier, and then it goes down to very low values. However, without the AGN, which is the dashed line, you see an upturn in the cosmic star formation rate density beyond redshift 0, which means that there would not be a finite amount of stars that's being formed in our universe. So our first task is to basically verify whether this is true beyond redshift zero or whether it's going to continue, whether basically there's upturn of star formation rate density beyond redshift zero. So we do this by first calibrating our simulations to redshift zero. That's important because we need to get our composition of the galaxies right at redshift zero. And the way we do this is to calibrate this to different properties which are presented by McCall et al. In 2010. So they had this observation of galaxies, and using their circular velocity, they constrain the amount of baryon matter in that should be in halos of different masses. So they looked at FD and F star. So FD is basically the amount of baryons as a function of the M500 multiplied by the baryon fraction, and the F star is the amount of stars. So essentially what this means is at redshift zero, the halo should contain the right amount of, we should calibrate our simulations to contain roughly the same amount of stars and gas that's being observed in McCall et al. 2010. So we did this calibration and we have the results that we show on the slide here. So on the left is again the FD against the M500. On the right is the F star or the FS against the M500. The blue dots are from the observation papers from McCall et al. 2010, and the black line is the fit that we've given to the observation. So we have simulation halos with non-zero star formation, and which are denoted by the red stars, and there's a black cross that denotes simulation halos with zero star formation. So obviously we're going to ignore those because those might have a variety of reasons why it's not forming stars. Maybe it's close to the edge of the refinement region, or basically the resolution limit. So if you look at the red stars and compare it to the observation, we can see that we reproduce an appropriate amount of the content in the halos at redshift zero. So with this as a starting point, we get the approximately right amount of gas and stars that should be in these halos, and now we can extend this further beyond redshift zero. And so we did this beyond redshift zero, and what we present here is a convergence test because we are running a we are running a simulation, so it's limited by resolution. So we need to know whether this resolution is appropriate for evolving our simulations beyond redshift zero. Of course, there are other details of tests that we've done in order to make sure that the simulations are able to go beyond redshift zero, and you can find all these details in the paper that are published in 2021. What we see here as denoted by the black circle is that there's a turnaround in star formation. And as we mentioned before, if there's a turnaround, it means that there's there's not a finite stellar mass that's being formed in the universe. And that is a problem when we want to proceed with our assigning the anthropic weights to different universes. So on the plot here, you see different labels of simulations. So NL is the fiducial, which is the green line. NL minus 1 and NL plus 1 is basically reducing and increasing the spatial resolution. And then the purple and the pink line, which is denoted by NLM minus 1 and NLM plus 1, is changing the mass resolution in the simulation. And the NLFB is basically changing a different feedback altogether. And we compare this to the black lines. Solid lines is the Maddow and Dickinson, and then dash line is the Baruzzi et al. 2013. So we have this, again, this peak at roughly around redshift 2, but we have this turnaround, which upon closer investigation, it seems to be proportional to the resolution. So the poorer the resolution, the earlier the turnaround. And when we looked at this in greater detail, we find that it's actually just a numerical effect. So we are convinced that our simulation is able to go beyond redshift 0 into the far future, and it's going to produce a similar trend to what Maddow and Dickinson presented. And that means a finite stellar mass that's being produced in the universe. So going beyond this, looking at the results, like I mentioned before, all we are concerned about is the total stellar mass that's being produced in each universe. And so when we change the different resolution and we look at the total stellar mass density, so by integrating the cosmic star formation rate density evolution, we get the excellent, reasonable agreement with observation, as you see highlighted in bold. The NL, when we improve the resolution for both spatial in NL+1 and the mass resolution in NLM+1. When you compare it to the observation, which is around 2.66 times 10 to the 9 for Madar and Dickinson and 2.13 for De Baruzzi et al., we find that our simulation is able to roughly produce the same amount of stars at redshift 0 by redshift 0. Sorry, beyond redshift 0 into the far future. So what this tells us is our resolution is enough and the subgroup physics that we have calibrated before is applicable and it's producing roughly the same amount of stars that would be expected from observation. So our next step is going into counterfactual universes because, like I said, we want to create the anthropic weights using the star formation rate or the stellar mass that's being produced in different universes as the argument for why observers would the anthropic reasoning basically. So if we look at this, it's basically the trajectories in which the cosmological parameters can lie on, assuming a flat lambda CDM universe, something like ours. So the dots represent the fiducial that we are working with, 0.3 for omega m, 0.7 for omega lambda, and sigma 8 of 0.8. So we apply the identical baryonic physics to all simulations, and we scale the box size and starting redshift so that by redshift 0, they all will all have the same amount of evolution. So we did this test for various universes, and here we have the lines. The dots basically represent the raw data from the simulation, and then the line is a fit using that functional form that we saw from Madal and Dickinson 2014. So we have different variables that are free parameters that we can fit this plot. And we ran two different sets of simulation, one which varies the value of lambda. So this one changes the lambda, and so the other parameters will have to change accordingly. And one that mimics the effect of changing lambda by changing the clustering of the matter, which basically what we're doing is changing the sigma 8, and that's denoted with a S prefix in front of the simulation. So with this, again, the functional form, we can fit the free parameters A, B, C, and D in order to quantify the amount of stars that form in different universes. So in the first column, you see the whole suite of simulations that we have, and A, B, C, D, the corresponding parameters that's being used. And then the R square is just a measure of how good the fit is when fitting A, B, C, D to the raw data from the simulation. And the closer it is to 1, the better the fit. So we can see they fit relatively well, except for the runs with the sigma, because they tend, especially when you go to higher and higher sigma. So when you try to mimic that for larger and larger cosmological constant, it's not going to follow the Madal and Dickinson plot as well. But assuming that everything follows that formula and we were to integrate this, we are able to get the stellar mass that's being formed in each universe. And we can see this on this plot. So on the y-axis is basically the star formation efficiency, the anthropic weights, if you will. It's basically the M star that's going to form in the lifetime of the universe, divided by the amount of baryons that's available. So we see the fits to the different simulations. So the red lines are fitted to the red line is fitted to the simulations with scaled lambda, and then the purple line is fitted to the simulations with the scaled sigma 8. And then we have the green line from John Peacock's work in 2007, and the blue line from Barnes et al. In 2018. So what we see here, the summary statistics is we find that using John's work for probability of observers living in universes that's similar to ours or less than with cosmological constant that's less than ours is about 0.082. So it's basically 8.2%. And in our simulation, we have a 12.9%. And so the median that we find is that ours is closer to one, not exactly at one, of course. It's we have basically we have significant suppression that we find using the simulation. And we might have better agreement between the two work using the theory and the simulation if a different critical mass is being chosen, which is 10 to the 12. And if we were to further plot this in terms of the probability of the alpha, which is the scaling of lambda to lambda observed that we see on the x-axis, we find that the highest probability is not at 1, regardless if you are looking at John's work, our work, or the Barnes et al. In 2018. Barnes et al. In 2018 predicts a median value of 50 to 60, and only 2% of observers will reside in a universe like ours. Despite using different models, we actually find that our two simulations approach make a fairly similar prediction about the value of the cosmological constant, or at least the median value. And this is, of course, not satisfactory. Maybe we can improve this agreement or this prediction of the lambda even further in our future work. But at least for now, we see that using two different galaxy formation model, we can get roughly similar prediction from those cosmological simulations. So in conclusion, we push simulation codes beyond their usual operating range. So as I said, people usually run these simulations down to redshift 0, and they are designed to reproduce observations at redshift 0. But we push it beyond their usual operating range, not just in terms of the time. So we go beyond our present time, but we also push it so that it operates in universes that it's very different, vastly different from what we are used to, which is the lambda CDM. And from our simulation, we find that 13% of the observers will live in a universe that has a similar value of lambda than the observed value that we have. And again, this is very similar to what Barnes et al. Had found in their paper. But the simulation is not perfect, and we can obviously improve these estimates. And one of the way is using metallicity weighted star formation. So the star formation here, it's very simplistic, and we just assume that the amount of observers is proportional to the amount of stars that's being formed. But obviously, to form planets, you need a certain metallicity. And so that can be one of the considerations to further improve the constraints. And in our simulations, we did not include black hole physics. These black hole physics are important because, especially for universes with very low lambda, so because structure formation will be very, very efficient in those universes. And if structure formation is efficient, obviously we need black hole physics in order to regulate the star formation. And up to this point, we have only considered positive values of lambda. There's no reason why we should ignore the negative n, except the extreme values, as we talked about in the introduction, as argued by Weinberg. So we need to have simulations where we investigate what happens when we have a negative cosmological constant and how structure formation is going to be different, and its corresponding star formation and the stellar mass, which would affect the anthropic weight. And of course, in these kinds of universes, black hole physics would turn out to be particularly important, as structure formation is highly efficient. So with that, thank you for your attention, and yeah, if you have any questions, please let me know. Thank you.